Hello, ladies and gentlemen, and also people named Kevin. Have you ever wondered what it's like to look at the numbers? I don't mean just the digits that we're all familiar with, like bit 1, 2, 3, etc. But I mean, have you ever wondered what it's like to look at all numbers at once, laid out before you, like as if on a map? Well, in July of 2007, I had this thought. I was wondering, what would it look like if we could see the characteristics of every number all at once? And so I thought about it for a bit and imagined it sort of like a quilt where you have different patches of cloth that get put together, sewed into a blanket. And so as I was picturing it in my mind, I thought of a ones column, which would be one square of cloth following another. And then next to it would be the twos column, where every other space would be cloth. And then the threes column, every third space, and the fours would be every fourth space, etc. It quickly became something that I could not picture in my mind anymore, but I realized that I had a tool sitting on my computer that would help me to actually visualize this, and it was none other than Microsoft Excel. And most people don't think of Excel as a graphing program, but it actually worked pretty well, and with just a little bit of time and effort and learning a bit of scripting, I was able to create what I call the factor field. All right, it's actually pretty easy to create a factor field using Visual Basic Script and Microsoft Excel. I do have Office 2007 on this computer. There will be some variations depending on the version of Office you're using as to what the specific values you want to put in here are. And when we get to that point, I'll show you. Let's just jump into the code really quick. So we'll start by creating our Excel object. And then we will need a workbook, which is part of the Excel object. Okay, actually, that just needs that. And then this will need a worksheet from the workbook. That one gets the one. And then let's make this visible. All right, and then we're going to want just some default values to start with. So it's going to be small samples. So we'll make the max width equal 100 and max depth equal 100. So this will give us a square 100 by 100 when we're done. And basically now we're done with the vast majority of the code. We just need to put in 2 for loops that will actually create what we're looking for. So the first one is going to be our column. We'll go from 1 to max width. And then each time we go through a column, I'm going to want to format the cell at the column to make it into a grid, so it has more of a graph feel than just letting it run in the default settings. So let's start by defining the column, and we'll make the column with 2.14. And you might wonder, where does this 2.14 come from? And that's just the value in Office 2007 in Excel for 20 pixels of width. You can find out how wide you need to make your number value by loading Excel, going in and clicking here in between one of the columns and just turning it into 20 pixels. It can sometimes be difficult to get to. But as you can see here, it says width 2.14 and in parentheses 20 pixels. So that's how you would find it on yours. Just find what that value is on your computer for whatever version you're using of Office. So what this will do as it starts every column, it will first format it so that the column width is exactly 20 pixels. And now we need the second loop, which does each row one at a time. And so this is the important part of the code. So what this will do is every row that it goes through, it starts at the number of the column. So the first time through, it's going to be equal to 1. And so every single one, it will go from 1 to the maximum depth and step 1. So that means every single row will be filled in, and then when it's done at the 100 mark, it'll loop back, and then it will start on row 2, but then it will step through it by 2 each time because the column is now 2. So every other cell will get filled. The third time through, it'll start on row 3 and then skip by 3, row 4, skipping by 4, etc. until we're done. And so what we're going to have it do is just take that cell, and using the scripting, you have to put the row first and then the column. And what we'll do is just change the background color here. And we'll set that to 1, which is equivalent to black. And then we're done with our 2 loops, and we'll just make it tell us that it's done when it's finished at this point. So the final step is we need to save this as a script, not a text file, and scripts have to end in .vbs, and so when we go to save it, we have to put it in quotes and just save this as factor field.vbs, end quote, hit enter to save this, give it a second here to pop up, and then we just run this, and as you can see, it fills out the factor field. And you can see it changing to make the columns the correct width. So it makes a graph, and if we just zoom out a little bit, then we get this 100 by 100 square of the factor field. So these are the first 100 values of the factor field. And that's how easy it is to make one.
All right, so I have a factor field pulled up here. This one goes 10,000 rows deep. We're not going to actually look at all of those, of course, but when we begin to look at the factor field, perhaps the first question we should ask is, why do we call this a factor field? Well, if we define each row as representing a number, then the columns represent the different factors of that number, hence the factor field. To give an example, let's go down to row 12. So what we're saying is that row 12 represents the number 12. And by looking at this, what we can see is that the column 1 is a factor of 12. Obviously that's true because 1 is a factor of all numbers. But here we also see that 2 is a factor of 12, and that makes sense because 2 divides into 12 6 times. 3 is a factor of 12 because 3 times 4 equals 12, which also is why 4 is a factor. But now we look at 5, and 5 is not a factor, so it should not have a cell filled in, and sure enough it doesn't. 6 is from 6 times 2, as we already mentioned earlier, so it must be in there. And then there should be nothing in between that and the number 12 itself, because 12 is a factor of 12. So looking at this, we actually have an easy way to find out what the factorization of a number is. If I just said, hey, give me the factors of 537, that would be a pretty difficult thing for you to just calculate, but if you just scroll down to 537, I went past it, there we go, 537, so we can look at this and go, okay, 1 is a factor, so is 3, and then continue way out there. And that one is going to be 179. So this is just an easy way of finding the different factors by just reading it off of this chart. When we look at this, there's actually an interesting pattern that emerges, and it gives us a second way to create the factor field. If you recall, the first time that we did this, based on the code, it was column by column. So we started with the ones column, where every single cell was shaded, every other row of 2, every third row of 3, and so forth. But there is another way that we can do it, and that's based off the diagonals. So we see here, starting at 1, if we go over 1, then down 1, over 1, down 1, we have this diagonal row, or this diagonal, I'll just call it a line. So this diagonal line just appearing there. And if you go to the 2s and do the same thing, only you move down 2, then over 1. So we got the second one down here, over 1, then go down 2, over 1, down 2. Every single time you go down, you end up on this second diagonal that has every other cell filled in. Same thing with the 3s, so you go down 3, over 1, down 3, etc. And you see that this third diagonal comes out, and it does it with every single other number that you do, 4, 5, 6, etc. So a second way that you could create the factor field is to actually do it on the diagonals, and you'll end up with the exact same representation that we have here. So this is kind of one of those reflections that are internal to mathematics. One of the things I love about math is how many times you can do multiple paths to get to the same destination. There's so many different routes to get to the same place. Sometimes it's easier to do one than the other. Programming wise, it's a lot easier to do the column method that I showed earlier, but it would definitely be possible to create this by the diagonals if you wanted to. So as we're looking at this, we already see that there's some interesting deep truths that we can start pulling from numbers. And I want to look over a few of the different properties of numbers that pop out from the screen here as we're looking at these further. The first thing that I want to look at is a feature that becomes really obvious if we zoom out a bit. So let me first start by zooming to make this just 10%. And then as we page down for a bit, we can see that there's these parabola looking features that appear, and they're very regular. As we page down, we slowly have them move towards the right, and they get wider and wider spaced apart. But they actually do exist clear up at the very beginning, and I'll go back to 100% right now to show that. So we can see one here, there's another one here, for example. And what you might notice is, we'll start with this first one, which is at column 3 in row 9. And if you know the relationship of 3 to 9, you know that 9 is actually 3 squared. And so it's no surprise that 4 squared is 16, and that's where another one of these points are. 5 squared, 25, another point, 6 squared, 36. So what we have here is actually a representation of where squares are. Knowing that, we can see that 2 squared being 4 is actually here. This is the little chevron looking device. It blends into the ones column, but it is actually there, and by that same point, 1 squared would also be there. Now what's really interesting is when we fill in what we have available here, we get to see some interesting patterns. So let me first show the ribbon again so that I can come over, and I'll start here, and we'll just put some background and we'll just turn it red. We'll do this really quick for this one. There we go. And then this will come up to here. There. And finally here to here. So this is where the whole parabola is for the one that has the origin at 6 squared equals 36. And what's interesting about this is that we can see there's a bit of a pattern if we do some simple math. We know, for example, that 5 times 7, which is here, equals 35, and that's the row that it's on. What's not as obvious, but it becomes obvious once you think about it, but it's not something you would immediately consider, is of course that 36 minus 1 equals 35. What this tells us is that we can actually find what a square is by multiplying 1 less than a number times 1 more than the number, and then adding 1 to that result. Now that sounds complicated, but essentially, using 6 as an example, if we didn't know that 6 times 6 equals 36, we could subtract 1 from 6 and get 5. We can add 1 to 6 and get 7, and know that 7 times 5 equals 35, and that is 1 less than what 6 squared would be. Another way to say that is to say n squared equals n minus 1 times n plus 1. All of that together, add 1 to that. Now that pattern actually continues through the next part. So we see here, this is column 4 times column 8, which equals 32, and 32 is indeed the row that this is on. Now what you might not realize here is that there is still a pattern between the 36 and the 32, where the result here was 1 less than the number n minus 1 times n plus 1. Here it is 4 less, so n minus 2 times n plus 2 plus 4 equals 36. And you might have already spotted the pattern. We'll look at this one where we have 3 times 9 equals 27. Now 3 times 9 is the same thing as saying n minus 3 times n plus 3, and now it is 9 away from 36. So the first time it was 1 difference, the second time it was 4, the third time it's 9, so the next time is going to be 16. Because what we're doing is, as we go further away, we are squaring the distance. So this is actually, the pattern that is coming up is actually the same as if we were saying n minus a times n plus a. All of that result added to a squared gives us the general formula, and that gives us every single one of these that start with this little chevron. So for example, there's another one here, and I'll put this in really quick. And there you go. As you can see, the same pattern exists here. So we have 5 squared. Well, 4 times 6 is 1 less than 5 squared. And here we have 5 minus 2, which is 3, times 5 plus 2, which is 7. That is the same as 21, which is, of course, now 4 less than 25. So that same pattern exists throughout this whole thing. And what I'll do really quick is just fill in these other ones. I'll pause the video and pick it back up once the other chevron parabolas are done. These are all filled in now. And you might notice there is another pattern emerging. All of these are ending on the ones column, but they're skipping. It's only showing the odd numbers. As you can see here, there seems to be another parabola that's in between, although this is a different origin. This has 2 characters side by side, and so we're going to look at that next. One of the first things that pops out is, of course, that these parabolas here seem to be right in between these other two. And if we trace back their dots, we can see that they appear on the spaces that are missing in between. So the question is, what would cause this pattern to emerge? Given that they are almost in the exact center between two of the squares, I theorize that we're actually looking at what would be the equivalent of a half square. So where this is 2 squared, then this would be 2.5 squared. Now, it itself is not the 2.5 square, because 2.5 squared is going to end with the 0.5 times 0.5, which means 0.25 is how it's going to end. And the factor field only shows whole numbers. If you could put the 0.25 in, it would be 6.25. 2.5 squared would be 6.25, and it would be right here. So what are these two numbers in relation to that square? Well, it turns out just as these two numbers can be viewed as n minus 1 and then n plus 1, all being 1 less than the square, here we can actually come up with a formula of n times n plus 1 plus the 0.25 equals our original n plus 0.5 squared. So it's a little bit complicated, but look at this equation here to see what I'm talking about. And you can see the math of why that works out. It does add up correctly. So what would happen if we filled in all of these half squares? What would we end up with? Well, let's just start by doing one of the parabolas here. So we'll do the background here and here. And then this one's going to be its own. So we come back over here. This one is related to these two, and then this and this. As you can see, we're beginning to fill in all of the missing points that we had before. So that's part of this one. We come over here, and this little parabola fills in these values. And there you have it. All of the numbers are being filled here. So the factor field can now be defined in yet a third way, which is as the whole number results of two equations. One being the n squared equation that we saw before, the other being n plus a half, all together squared. I'll call those half squares for now. So if you take all the square numbers, the perfect square numbers, and all the half square numbers together, get the whole number results, graph them, you have the factor field emerge yet again. So the factor field tells us not just information about prime numbers, not just information about the factors of numbers, but also it tells us where perfect squares are and half squares in between those perfect squares. So this is some pretty amazing stuff, as we can already see. And as I was getting ready to do the next section of the factor field, which is going to deal with reflections and repetitions, I was looking at this particular row, 5040, and I actually discovered something interesting related back to the squares that we were just going over. First of all, we can see over here, there is a square here. 71 squared is 5041, so this little parabola is part of the squares. But when I was getting ready to look at this one, I discovered this thing here, which is another parabola, but it's stretched out. And I was wondering, what is this? So I pulled up a calculator. This is on the 41st column, and it equals 5043. Well, 5043 is equivalent to 41 squared times 3. And if you notice, there's 3 in between these values, where the next one comes in. So this is a square, but it's stretched by another factor. What's interesting is that as we continue up to here, the differences between this and this is 9. And so the first time it's a difference of 3, then it's a difference of 9. And if we look up even further to the next one up here, it's a distance of 15. And so you can see 3 times 1, 3 times 3, 3 times 5. So 3 times 7 would be next, and it is indeed a difference up here of 21 to this next point. So the factors as it's stretched here is increasing by multiplying it by 3 times every odd number, stretching it out a ways. And so I think that fits back with the squares that we were looking at before. If you remember, they all hit on the ones line every other row, and so it was all the odd ones. So here it's stretching it out by a factor of 3 each time, doing 3 times 1, 3 times 3, 3 times 5, 3 times 7, etc. So this is just something that I just discovered here while I was getting ready to do this next section, which I found kind of interesting. In any case, what I want to talk about for this next portion is the fact that the factor field itself has reflections and repetitions within it. So I picked this row intentionally because this gives us 10 factors at the very beginning. It gives us a long line here. And what's really interesting about this is you can see that for these 10 columns, it is a perfect reflection up and it repeats down. So if we just highlight this whole thing here, and copy that, I'll go back up to the top, and I'm just going to paste this over here for now so that we can see it here. Now what's interesting is if we take this and go down to the first 10, copy that, and then come over here, paste it there, you can see this is a complete repeat of what came before. So when we have this bar across the top, then everything below it, for as long as that bar goes, repeats what the initial factor field was. And then above it, it is a reflection of what follows afterward. And it makes sense when you think about it, because if you remember, these were columns that were created through loops, and if this cell is filled, then because it's in the second column, then this cell has to be filled and this cell has to be filled. It can't be otherwise. Same thing with 3. There has to be 3 up to there, and then 4 to there, etc. So as long as there is a bar across the top where every single factor is in place, then it will repeat exactly what the factor field is below. Now that has some radical implications when we consider the factor field as a whole. Now the factor field started at 1, but imagine if it had started at 0 instead of 1. Let's just pretend for the sake of argument that the header here in Excel is the 0 row. Well, we would know that this cell would be filled, but then the next 2 up would make this filled, and then the next 3 up would make this filled, etc. So this whole thing would be filled across. And it makes sense mathematically when you think about the number 0. Every number could divide evenly into 0, and therefore every number can be viewed as a factor of 0. But 0 is not the only number that every number could be factored into. I'm going to introduce something that is a bit controversial here, but if you pay attention to how things are structured, then what I'm going to say makes sense. I think it makes sense in the same way that it makes sense to say that I, which is the square root of -1, makes sense in math. We can use that even though technically we can't have a negative number as a square root. I squared equals -1. That violates the rule of exponents, and yet we need that for math to work. In the same way, I'm going to violate a rule of math here, but in a way that I think is insightful. It's not just making up something, it's giving a profound theory, a profound understanding of what's going on. And what I'm going to claim is that we can take a certain type of infinity. That infinity I'm going to call infinity-factorial, because it is defined specifically as the factorial of all natural numbers. That would be 1 times 2 times 3 times 4 times 5, all the way up. Given that specific definition of this particular infinity that we're looking at, which is not equivalent to all other types of infinity that one could look at. For example, you could have the infinite set of even numbers. That would not follow the rules that we need for this. But if you take infinity factorial and consider for a second what that would be if you could add 1 to that number, and of course infinity is not a number, but go with it for a second. If you took infinity factorial and could add 1, what would that be? If that could be an actual number, we know that infinity factorial plus 1 could not be divisible by 2, because 2 is a factor of infinity factorial. It's 1 times 2 times 3 times 4, etc. So the next number that would be divisible by 2 would have to be infinity factorial plus 2. Infinity factorial plus 1 is not divisible by 2. Likewise, it's not divisible by 3, or 4, or 5, or any other number. The only number that infinity factorial plus 1 could possibly be divisible by is 1 itself. The graph that would be made, if we graph that, would look exactly the same as the current factor field that we have here. This would be the only value that it would be divisible by. Infinity factorial plus 2 would only have these 2 divisible factors, nothing else. In other words, in some sense, the infinity factorial plus 1 is equivalent to the number 1, and therefore infinity factorial itself is equivalent to 0. Now, as I said, I understand this violates a specific rule that you can't add or subtract to an infinity. But if you think about the logic of this, rather than thinking of it as a number, think of how that number is constructed, and then imagine it just as we do with the square root of -1 being I and becoming a useful thing. Then there is something in mathematics where infinity somehow loops back on itself and goes back to 0. What is happening in that? It's a jump in the math that we can't really understand, but if we think about it from the factor field for a minute, there is no functional difference between the graph if 0 is mapped on it, or if infinity, defined as 1 times 2 times 3 times 4, etc., is graphed on it. So infinity factorial and 0 give us the same exact graph. Now, from the rules of geometry, we know that if two triangles are congruent with each other, then those two triangles can be viewed as equal. In that sense, because infinity factorial is congruent with 0 as the starting point, the graph that you get is identical in both. Those two graphs are congruent, so in some sense, at the geometrical sense, there is an equivalency between infinity factorial and 0. I think that ultimately this will have some profound effects on mathematics as we move forward.